Okay, hi everyone. So for this video, basically, we will discuss on the remaining parts of chapter number 3, intensity transformation and spatial filtering. So in this video, the focus will be given to this one, spatial filtering. So whereby the neighborhood of each pixel will be the dominant things that in this particular discussion. Not to forget that we will use several background and fundamentals of spatial filtering. So spatial filtering is used in a broad spectrum of image processing application. So a solid understanding of filtering, so whereby the keyword over here is filtering principle is crucial. Okay, right. So filtering in the layman terms basically take something and avoid something. There will be filtering. So in the technical perspective, whereby the filtering refers to passing mode. This one is frequency, for instance. Okay, so this one is a frequency. So speaking of the whole range of frequency, so low pass meaning this area, and okay, so this area will be allowed, but this area doesn't be allowed. Sorry, rejected. So this one, okay, reject. So that would be low pass. Okay, the net effect produced by low is smooth and image by blurring it. So normally the blurring effect will be causing at the end of the stage of low pass filtering. Okay, we can accomplish similar smoothing directly on the image itself by using spatial filter. So spatial is probably dedicated for this particular parts in this chapter, right? Okay, for fundamentals of filtering, at the same time, the spatial filtering modify an image by replacing the value of each pixel by a function. Okay, so the keyword here is replacing a value using a function of value. Okay, regards to the pixel and its neighbor. Okay, replacing. So the function is basically manipulating or replacing the value of pixel and neighbor's pixel. Okay, if the operation performed on the image pixel is linear, then the filter is called linear spatial filter. So otherwise the filter is non-linear, then they call it non-linear spatial filter. So that will be straightforward of the categorization for the spatial filtering, linear and non-linear. So but the majority, at the end of the day, the majority of the one that we discuss in this particular video will be linear spatial filter, right? So a bit of introduction to linear spatial filtering. So by any means, the first thing first is a kernel. Okay, so kernel likewise it will be called as W over here, omega. So a function that been inner product of the images. Okay, it's not this one, by the way. So inner product of these two. So the kernel multiplied by the image itself. So the mechanics over the linear spatial filtering by 3 by 3. So 3 by 3 kernels over here reflecting to the blue box over here. So meaning 3 by 3. Pixels are shown as square to simplify the graphic. Note that the origin of it is the top of the left. Okay, so whereby the top of the left will be the origin. By replacing the origin of the center spatial symmetric kernel, supply writing expression for the linear filtering. So this will be discussing later on. So we have correlation and convolution afterwards. So we have two examples to be discussed for today, and we'll be discussing on that matters later on. Okay, so a bit of the mathematical perspective in linear spatial filtering. So linear spatial filter performs sum of product. So whereby this will be the sum operation between F and W omega. Okay, so whereby this one is the image, while this one is kernel. So the one that we did talk about just now is the 3 times 3 kernel with the inner product for the image. Okay, so inner product is this one, I guess. Okay, so the kernel is a array whose size defined by neighborhood of the operation whose coefficient determine the nature of the filter. So basically, by defining the kernel itself, that would be the nature of the filter later on. So likewise, we have many types of filters. So we have Gaussian, we have low pass, high pass, and band pass, and so on. Okay. So in this particular discussion, so some of the reference refer the filter kernel as a mask, and also template, and also window. So whereby this terminology will be the same discussing on this one. Okay, but in this discussion, we will stick with 2, filter kernel or simple as a kernel. So reflecting to this omega. Okay, so G is basically the output after we applied the kernel with respect to the F original images, right, as the input or the general perspective, right? Okay, in this spatial filtering system of spatial filtering function, we have 2 things to be discussed right now, whereby we will discuss the correlation and convolution. So in order to talk about the correlation and convolution respected to the spatial filtering, so there are 2 things will be given. One is F, one is omega. So the things that have been given to us as a kernel right here is 1 times 5. So whereby the M times N is reflected to size of kernel, whereby M is 2A plus 1, N is 2B plus 1. So when we talk about A is 2, so 4 plus 1, so 0 plus 1, right? So whereby we have 5 and 1. Okay, so 1 plus 5, so that would be this one. Okay, so this one is 1 plus 5, while this one is 2, 4, 6, 8. So 1 times 8 origin image in terms of pixel. So B is showing the starting position. So normally the starting position for that particular correlation is happen to be as here, here, guys. Okay. So but the thing is, we need to be careful. The center of the kernel need to be multiplied by the what they call it, the first digits or the first value of the image F. Okay, since we have we don't have enough value over here, and what we call it at the end of the day, when we move this particular kernel to the end of the line, so basically we still exhausting 2 digits, 2 binary number over here. Okay, so then what we do is the things we tend to have the pixel at the front of the back, and to fit the back and the front over here, what we call it padding. So padding is basically the solution for giving a pixel in a full length towards the kernel. So in order to make things clear to the kernel, basically we have this one equation to put how many 0 in our original F alias images. So like in example, we have 1 over 5. Okay, so 5 minus 1 over 2 means 4 over 2. So what we have is 2. So 2 should be added to the beginning and to the end of the configuration for the F. So that's the reason why in C we can see that 0, 2 places and 0, 2 places at the end and the beginning has been added, right? Okay, so after we gain the idea of the zero padding, so we shall start the correlation by using this equation. So because of this -2 is basically reflected to this value, guys. Okay, and 2 is this value. So because -2, -1, 0, 1, 2, so there will be 5. So that's the reason why the things need to be done by here. 0, -2, -1, 0, 1, and 2. So W is for S -2. Let's say this one is F -2 plus 1. So -1, F minus 1 plus 1, and etc. So that would be the calculation of the inner product for the G0. And this will be following by G1 until 1, 2, 3, 4, 5, 6, 7, 8, 8, right? So we have this one is okay, this one is 0, 0. So until we have this one is become 8, and this one become 2, this one become 4, this one become 2, become 1, right? So at the end of the day, we have this particular results, right? So after we move the kernels from the left to the right, so we shall have this one as 0 for the first, second, third, fourth until 8. So but in terms of considering the heading pixel as an extent of full correlation result, so this one would be the result that we have. Okay, so that would be the extended version. So right, the correlation is just a things that we don't manipulate the kernel itself, but we add something to the front and to the back if the pixel for the F doesn't really fix with the kernel, right? So let's go to the spatial convolution. Okay, so right, in convolution, the idea was the same. The padding is the same. We add the front 2 and at the back 2. So but the things happen when we talk about convolution. Convolution is happen to be as this one. Convolution is in Japanese they call it this one, tatami komi. Okay, so the idea is we try to put it upside down, so meaning 8, 2, 4, 2, 1 would be 1. The original is 1, 2, 4, right? So 1, 2, 4, 2, 8 will be reflecting to not this one, by the way. The most back value will be the front, the second will be the second front, the fourth will be the third, and the second will be the second, and the first will be the last. So that will be convolution. So whereby we try to move this n to n minus lambda. Let's say lambda is the one that we are talking about. Okay. So then the thing will be the same. We try to start from here. Okay. So 0, 0. This one start from this, and this. Okay. And at the end we will have the final the value for convolution result as 0, 1, 2, 4, 2, 8. There will be opposite way of that particular things that we gain in the correlation, right? Okay. So remember, to the extent of the extent of convolution result will be added the two beginning and to the end of the given F, right? So that would be a full convolution result, and this one is the conventional convolution result. Okay. Right. So this one is for you guys do it at home exercise. So try this for the both cases, correlation and convolution. Considering f is 5 times 5. So this one is f, guys. Okay, this one is image. And 3 times 3 kernel. Okay, so basically this would be the final answer for those situation. But all the thing is how we do it. Okay, so that would be the same as correlation. We just padding without changing the W or the kernel. On the other hand, for the convolution, we just padding. And remember, we need to reflect the n to n minus lambda, right? So we need to transpose them into the opposite way of the kernel, right? Okay, so that would be as your homework to do at home. And okay, so after the spatial correlation and spatial convolution, so we straight away jump to the another kernels, smoothing kernel. So we have a normal smoothing kernel. We have two in this discussion. One is box and the other one is Gaussian. Okay, so box kernel is simple. So let's say 3 times 3. So that would be a box, but Gaussian kernel is depending on the Gaussian function. So whereby if we look at the 3D dimension over here, so this is this, while this one is the how to portray this, meaning, so the kind of hill. Okay, so this one is this area, this one is this one is that, and this one is the remaining parts, right? Okay, that would be Gaussian. So smoothing is to basically to apply to the imaging f by using this particular tool, right? Okay, so there will be some example of the kernels. I think there will be a separable kernel type. So separable kernel type, in order to have this particular kernel, let's say 2 times 3 kernel, so it could be produced by combining two kernel C and RT. So at the end we have one single kernel. So that would be kernel with the separable one, okay, to the C and R. So that would be another different separated kernel types. Okay, so how the spatial filter kernels are being constructed is basically by the 3 approaches so far in this class discussion. One of those is formulating filter based on the mathematical properties. So whereby it depends on the A or B, A or B, or A and B, and so on. Mathematical properties, or summation or subtraction, and so on. So the second approach will be the 2D spatial function step. So one of those is Gaussian function. So Gaussian is dedicatedly came from the Gaussian function. So whereby we have the 3 times 3. So 1, 0 is the middle. So the highest hill at the Gaussian function, right? So the third approach is the spatial filter with a specific frequency response. So whereby this approach is based on the previous section and fall into the area that digital filter design. So it depends on, likewise, the box filter, right? Okay. Okay. So smoothing is basically averaging kind of thing. Okay. And it used to reduce the sharp transition in intensity. Okay, sharp transition meaning if we have this level of intensity, kind of sharp. It's not like this is low transition, right? So the act of smoothing is basically reducing the effect of the sharp transition. So because the it will be averaging the high and the low one, so whereby we will have a kind of average intensity pixel value after we apply the spatial filtering. Okay, so to reduce the irrelevant details, whereby the irrelevant is kind of a small respect to the size of the filter kernel. So normally that would be this would be the issues, because sometimes it is not relevant when we compare to the size of the filter kernel, right? So another application for the smoothing, using the insufficient number intensity level for any in one particular image. Okay, so we have several types of smoothing. We have low pass filter as a fundamental, whereby we can expand them to the sharpening using the high pass, band pass, and bands reject, and so on. Okay, so this is the example of low pass filtering with a box kernel. So the box kernel is the first one, the one that we discussed earlier, this one. Okay, so whereby we have the box kernel for 3 times 3, 11 times 11, and 21 times 21. So this one is 3 times 3. This one is 11 times 11. This one is 21 times 21. As the kernel size increase, meaning the box kernel, so we can see that the flow of the blurriness of the images become clearer. Okay, so this one is blur. So I think 3 and 3 is much better compared to 11. So the 11 started to be blurry somehow. So especially the curving and this line, right? So compared to this, so things started to be looks like blurry. Okay, okay, low pass Gaussian filter kernel. Okay, so this one, the one that I tried to sketch it down just now. So we have GST over here. So this reflected to here. So the other one is here, there, this, and that. And while the remaining part is this 0.3679. Okay, at the how to say, this one example, this one is south, this one is southwest, right? Okay, and by using the Gaussian kernel, B is 21 times 21, so this one is 43 times 43. So still, by using this 21 by this one, and the sigma is 3.5, this would be the result of the Gaussian. Okay, slightly better than 43 for if we are using this one. So this one is the changeable constants, which available over here. Okay, right, for the Gaussian kernel. Okay, so there are several application for the low pass filter. So one of those is happen to result the galaxies images. Let's say this one is try to portray this to be in a less components in images compared to this one. So because they will be reducing this small stars at the galaxy. So same as this one too. So, and then the other application was the removing the shading in the pattern style of images. Okay, so we can see over here, this would be the patterning, and plus the shading over here and over here, right? So similar as this one. Okay, so after we try to use the low pass filtering, basically we can remove the shading and we have this as a result. Okay, Okay, median filtering. Median filtering is the one of the noise reduction, especially for the semiconductor factory application. So B is 19 times 19 Gaussian low pass, while the C is 7 times 7 median filter. So you can take a look at the way that the quality is. Okay, it depends on the application. So yes. Okay, so sharpening is happen to use high pass filter. So sharpening highlights the transition in intensity. So the keywords here is okay. So use the image sharpening range for electronics printing and medical images. So basically they will try to push it up at the high intensity as they could. Okay. So blurry is happen in averaging, but the sharpening is happen to the in order to highlight the transition. Okay. So especially when we talk when we take a look at this image sharpening using the Laplacian. Okay. So the A is the blur image for the North Pole. So this one is North Pole. Okay. But the thing is, when we apply the BCD, so Laplacian sharpening with C-1 and sharpened using same produce but with the kernel. So we can see the Laplacian is still obtaining the kernel, and we can see the result by having this kind of images. So compared to this and this, there will be difference. And D is basically the sharpening using the same procedure but with a kernel. So take a look the difference between these three. Okay, so this one and this one, I think this one much better compared to this area. Okay, so that would be the benefit of using the image sharpening when we need to have the high intensity transition, right? Okay, speaking about the unsharp masking and high boosting filtering, so this would be the one. So imagine that we have a blur one as a A. So at the end of the day, this will be the result in order to high boost, okay, of that particular given image, deep XE, right? And there'll be some example for the sharpening. That would be the gradient. So this one is just example 3 times 3 cross gradient operator. So this one is robots, and this one is for robots, and this one is Sobel operator. Okay, right? So respected to the gradient for those particular given image profile or image pixel. Okay, right. So by using that previous gradient for the edge enhancing, basically we can see, especially in order to see the defect of production line. So example, this one is the production for contact lens. So we can see, okay, boundary at 4 and 5. This one and this one, right? So we can see this one is happen to be detected as a defect, okay? In this particular gradient edge enhancement. Okay? So this one is an example for the high pass, band reject, band pass. Okay, regarding to the given image here. So this one is the way that filter type low pass, band reject, and band pass in a spatial kernel in terms of low pass kernel LP. Okay. So by using the low pass, we can describe the high pass. By using the low pass, also we can describe the band and reject. Okay. So this one is the just an example presentation for how we combine the spatial enhancements methodology using, this one is for a low pass, high pass. This one is the image. B with the intensity scale. Okay. This one is reject. Result, reject, band reject result. This one is band pass, and this one is the E, okay, with the intensity scale, right? So that would be the how we can see the differences between spatial enhancement methods for A to F. All right. So if we try to combine the spatial enhancement method, so let's say this one is the body bone scan. By using the Laplacian, we have this. So that would be totally difficult to recognize. But we only have this kind of reflected pixel for the bone, okay? So while the C is basically the sharpening image obtained by A and B, okay? This one, getting C. While D is Sobel gradient of the image of A. So this one is from A, okay? So that will be a better dimension to see the bone by using an image. Okay, right. So this one is E, F, G, and H is different technique to be combined as a spatial enhancement method. So E is Sobel smooth with the 5x5 box filter. So whereby this one is Sobel. This one is improving the D using 5x5 box filter. Okay. So the F is B and E. Okay. So the mass perform product of B and E. So this and the upstairs B. And this one is the sharpened image obtained by A and F. Okay. So where is F? This one and this. Okay. So but not to forget, the final answer is a final result obtained by the power law transmission. So remember the one that we did discuss in the previous video, to the G. So this one is power law, or we call it gamma. Okay. And we have the H. Okay. So at the end, we can see the how perspective, or how which application that we want to use to see and utilize the spatial enhancement method. So if we take a look at here, there will be a special needs, like we can see the range of the body thickness with the bones. So this one is slightly reference, and this one is just focusing on these parts. If you take a look, the major parts of the bone. So it depends on what application that we want to use to apply such a spatial filtering in image processing. So I think that's all for this particular discussion. It just explaining about the example for the spatial filtering. So I hope you guys can rewatch the video, and see you guys in the next video. Bye. Okay, thank you guys for watching NMZH channel. Hopefully you can get knowledge and benefit from the videos. Thank you so much. Assalamualaikum.